All right. So now in this video, we want to continue on with our idea of conservative vector fields and this idea of independence of path. So we want to know when a vector field is conservative. If we do know that, then we can apply our fundamental theorem for line integrals, which is very nice because it allows us to just calculate the line integral by finding the evaluation of the scalar function f at the endpoint of the curve C minus the evaluation of the scalar function f at the initial point of the curve C. So, really our question becomes, again, how do we determine if a vector field is conservative? Because we want our vector field to be conservative. If it is, then we have an easy way to solve our line integral over the vector field. So how do we do this? Well, let's suppose we have our vector field f, and this is some pi plus qj. Let's suppose that is conservative. If so, what does that mean? That means there exists a function f where the partial of f with respect to x is p, and the partial of f with respect to y is q, because this is supposed to be the gradient of f. Okay, and the gradient means in our first component we get partial of f with respect to x, and our second component we get partial of f with respect to y. All right. Well, by Clairaut's theorem from back in chapter 14, the partial of p with respect to y is equal to the second order partial of f with respect to x first, then y. And Clairaut's theorem is also called the mixed partial. So this is actually equal to the second order partial of f with respect to y first and then with respect to x, which is the partial of q with respect to x. Okay, so this is true if p and q have continuous first order partial derivatives. All right, that's what Clairaut's theorem says. All right, so this gives us a way to determine if our vector field is conservative, right? So what we want is really the converse of this statement, right? So our statement was if f was conservative and this p and q were continuous first order partials, then the partial of p with respect to y is equal to the partial of q with respect to x. What we would like is the converse of that statement, or in other words, if partial p with respect to y is equal to partial q with respect to x, then that tells us that this vector field f is a conservative vector field. That's what we would like. Okay? And so, to be able to say that, we have to come up with a few more definitions. Sorry about all the definitions, but that's where we're at in this semester. Okay. So, one thing is, first, we have to define something called open, or an open set. Well, you can think of a set as open if it does not contain any of its boundary. What is its boundary? Well, if we have a region like this, the boundary is just the outer part of this region. So an open set is if we didn't include that boundary. So if I had some R here, where we have a region, but we don't include those boundary points, so I'm doing dotted lines there because we're not including those points, well, then this would be an open set. Okay? So that is our definition of an open set. We also need the definition of a connected region. Well, a connected region is a region that you can draw a line in that region between any pair of points in that region. So what does that mean? That means, for example, here, if I have this region here, this is connected. If I draw a point here and I draw any other point in this region, I can always draw a line between those points that stays within the region. An example of a not connected or a disconnected region is something like this picture over here, where if I draw a point here and I pick maybe a point over here, well, now there's no way I can draw a line that stays within the region that connects between those 2 points. Because to get from here to here, we have to go outside of our region. So this is a non-connected region or a disconnected region, and this is a connected region. Now again, we defined those because I have a theorem for us. Oh, very soon. We have one more definition first, but we have a theorem coming up soon that will help us determine when our vector field is conservative. Okay? But before we do that, we have one more definition, and that is that a set D is simply connected if every loop in D can be connected, or can be contracted to a single point. Okay? So this right here is a picture of a simply connected region, because if I take any closed loop in here, I can contract that in. I can squeeze that loop in to a single point within our region. Notice that if I get a region that looks like a donut over here, so we have a hole in the middle, that's no longer true. I could have a loop over here, that loop I can definitely contract down to a single point. But this needs to be true for every loop, and so what if I thought about this loop here? Well, I can't contract this down to a single point without leaving the region. So, because of that, we call this a not simply connected region. So, over here we get simply connected. Here we get not simply connected. Alright? And now, those may be strange definitions, but it turns out they're very important for this idea of a conservative vector field. So let F be a vector field, Pi plus Qj plus Rk. And this is a field in an open, if this is a vector field in an open, simply connected domain whose component functions have continuous first-order partial derivatives, then it turns out the F here, this vector field F, is conservative if and only if these three conditions happen. And that is the partial of R with respect to Y is equal to the partial of Q with respect to Z. The partial of P with respect to Z is equal to the partial of R with respect to X. And the partial of Q with respect to X is equal to the partial of P with respect to Y. If all three of those things happen, then F is a conservative vector field if we are on an open, simply connected domain. Well, that's a lot. And we're not going to prove that at all. That is well beyond this class. But it does give us a way to determine if F is conservative. Now, moreover, notice that if we are just in 2 dimensions, so we don't have a third dimension R of k here, then we actually don't have these first 2 equalities, and we only have to satisfy this third equality. So we only have to satisfy the partial of Q with respect to X is equal to the partial of P with respect to Y. And that will be true if and only if F is a conservative vector field. All right, and we'll go ahead and end this video here. The next video will just be 2 examples of how to determine if a vector field F is conservative.